Hello everyone, my name is Karan Gaikwad. Welcome to the Week 5 project presentation for Advanced Structural Mechanics. The topic for this week's project is verifying the divergence theorem. As you can see that the body I've chosen is a table lamp, which is a combination of a hemisphere and two cylinders with varying radii. Coming to the vector field that I've chosen is kind of different. It can be imagined as the expansion of my composite body in the transverse direction. It's not the usual deflection one which you could see in Professor Prakash's presentation. So coming to computing the divergence is given by the partial differentiation of the vector field with respect to x1, x2, and x3. In this case, x1 and x3 pan out to be 0, and the only term we are left with is the middle term, which comes out to be 2 sine x2 by phi h the whole divided by 25. These are the parameterizations that I've used for defining all the three bodies. The first one is for the hemisphere, this is for the cylinder, which is at the middle, and this third one is for the cylinder at the base. So I've substituted the value of x2, which is r sine phi sine theta, into this function right here, which gives out to be this. Similarly, I've substituted the values of x2 for the cylinders as well into the function. Coming to computing the left hand side of the divergence theorem, which is basically the volume integral. This is the expression that I have come up with for the hemisphere, which comes out to be quite complex to do it by hand. So I've used MATLAB to find out the value of the integral for the hemisphere. So which comes out to be 8.5767. I've substituted the appropriate limits for the radius, that is 0 to 11, for theta 0 to pi, and for phi, which is pi by 2. I've done the same thing for calculating the volume integrals, I'm sorry, for the cylinders at the middle and the top. So these are the values that are obtained from MATLAB. So the total comes out to be 11.5925, which can be verified over here. Coming to the right hand side of the divergence theorem, which is basically what we need to do in MATLAB. So I've substituted the appropriate values of x2 in the vector field, which is given in the first slide, that is this one. So x2 for the hemisphere is r sine phi sine theta. I've substituted the value of x2 for hemisphere right here and multiplied it with the normal sign vector in MATLAB. I've done the similar thing for the cylinder and the base cylinder as well. So the total computed by MATLAB comes out to be 11.777, which is different from what I've obtained, which is 11.59. So it's just a 1% error, which is fine, I guess. So this is my MATLAB window output. Coming to the MATLAB code over here, just a second. So coming to the MATLAB code. So this is my MATLAB code, and let's run it. So yeah, this is the vector field that I plotted, and this is the value of the scalar field, which is basically the divergence here in this case. And this is my composite body, and this is the output of the MATLAB code that is given. So that's all for this video. Thank you so much for watching. Have a good one.